Hello everyone, I'm Ali Ajos from University of Poitiers, France. The title of our paper is Collision-Free Formation Tracking of Multi-Agent Systems Under Communication Constraints. Here's the outline of the presentation. I will start with brief introduction and then we'll be giving problem statement, main results, and we'll be showing some simulation results as well. So nature is full of examples of species using formations to accomplish complex tasks. For example, birds fly in a V shape to reduce the drag force. Similarly, ants make different geometric shapes to basically move heavy chunks of food to their underground nest. So, inspired by these examples, researchers have basically produced some applications of formation. For example, fighter jets make a formation while going to attack their enemies. Satellites are in particular formation to cover the maximum area of Earth. And drones and robots is another area of application of formation, where robots are deployed in defense, rescue, exploration, and terrain purposes. To control the behavior of a multi-agent system, there are basically two schemes used. The first one is known as centralized control scheme, where a central unit is responsible of controlling all the agents. The agents send their information to central control unit, and then central control unit compute the control input and send it back to the respective agent. There are some serious issues associated with centralized control scheme. For example, if the number of agents are increased, then the computation load on the central system is increased dramatically. Moreover, if central control system is failed, then whole system will collapse. The other one is known as distributed control scheme, in which there is no central unit and agents communicate with their neighbors in the network and then compute their control input based on the information they receive from the neighbor. And since there is no central unit, so and the computation is divided among the agents, so number of agents can be increased. And if any agent is failed, then remaining agent won't collapse, but they will continue doing their work. So that is why it is more efficient, robust, and scalable strategy. So in formation control, agents are required to start from their initial condition and to reach to some position to make a desired geometric shape. In some cases, agents are not only required to uh, make a geometric shape, but they are also required to follow a certain trajectory while maintaining that shape. And this is known as formation tracking. The reference trajectory can be produced by a leader, uh, which could either be real or virtual. So let us consider that a multi-agent system consists of n followers and a leader, and the dynamics of ith follower is given by 1, where pi is the position of agent I, vi is the velocity, and ui is the control input which we have to design to achieve the desired formation. The dynamics of the leader is denoted by 0 and given by equation 2. U naught is the input of the leader, and it is independent of all other agents in the network and can be designed to achieve any reference trajectory. U naught has only one condition, that it should be bounded by some upper bound. We consider various communication constraints, which are very practical. For example, each agent can only measure and transmit its position information. It cannot measure or transmit its velocity as well as acceleration or input. So this is very practical constraints, because to reduce the cost of an agent, it is not usually equipped with all the sensors. And sending partial data is also cost effective in sense that it will require less communication bandwidth. Secondly, we consider that the sampling periods are irregular and asynchronous. So asynchronous mean that the sampling periods of agent one does not do not depend on the sampling periods of other agents in the network. However, the sampling period must be between some maximum and minimum value, and we consider only direct communication topology. The formation shape can be described by a formation vector f, where FIP is basically the position offset of agent I with respect to the leader. So any shape can be defined by defining the position offset with respect to the leader. Here are a couple of important definitions. The first one is about practical formation tracking, which says that the formation tracking is solved practically if there exists some small positive number and the error xi minus fi minus x0 is becomes less than that positive number epsilon bar as time approaches to infinity. The collision is said to be avoided if the inter-agent distance remains greater than 2r, where r is the safety disk around the agent for all time t greater than equal to 0. So the idea is to use a trivial controller in continuous time. However, since we have only position that is also in discrete time, so we will be using continuous discrete time observer to estimate the position and velocity values in continuous time. So here is the controller, formation controller, where C bar is the coupling strength and lambda is the controller gain, and position and velocities are estimated using the observer 6 and 7, where theta is the tuning gain of the observer. The collision avoidance mechanism is designed based on the potential function. Basically, potential function can be used to to incorporate a repulsive force between the agents when their distance is less than some threshold. So consider that each agent has a protection radius of small r and detection radius of capital R. Then the potential field can be defined like this based on the inter-agent distance. Pij is in fact the distance between agent J and agent I. And we can see that with this graph that if the distance between the agent is decreasing, then the potential field is increasing, and potential field becomes zero if the distance between the agents is greater than capital R. So the total repulsive force on agent I can be described by UIR and given by this equation. So now the overall controller will be sum of formation controller and the repulsive controller. So the theorem says that if we have a second order multi-agent system, as we described earlier with this controller, and if controller gains satisfy the following conditions, then we will have the formation tracking solved in practical sense and the collision is avoided. These conditions on the gains are derived through Lyapunov stability analysis. So these are sufficient conditions. We can see that the theta is inversely proportional to the maximum sampling period tau m. So if the maximum sampling period is high, we need to choose theta relatively low, and lambda should be smaller than theta because we should our controller dynamics should be slower than the observer dynamics. So for simulation purposes, we consider a multi-agent system with 4 followers and a leader, and tuning gain are chosen as theta is equal to 10 and lambda is equal to 0.6. The sampling period is between 10 milliseconds and 200 milliseconds. Protection radius is 0.25 meter and detection radius is 2 meter. For the formation shape, we consider a square shape around the leader. So here is a simulation result in which agent started from the initial condition and avoiding the collision and eventually reaching to their desired position to make a square pattern around the leader. So here is the distance of follower 1 with respect to all other agents, and we can see that the collision is avoided since the distance between the agents is always greater than 2 times of the protection radius. And we can see as soon as the distance between the agents become less than the detection radius, the repulsive force acts and repel the agents in opposite direction, and the distance, as soon as the distance increases, then capital R, the repulsive force become zero. This is an example of sampling time between the agents, and it can be seen that these sampling instants are totally irregular and asynchronous. We have also applied this formation tracking algorithm on a fleet of mobile robot using robot operating system and gazebo simulator. In the first scenario, the leader is static and all the followers are required to make a formation, scare formation around the leader. And we since these kind of robots have non-holonomic constraints, we use flatness properties of the robot to apply our designed algorithm on such robots. And in the second case, the leader is moving with some velocity, and the followers will make a square shape while avoiding the collision among them, and then maintain this square shape even the leader is moving. So here the square shape is maintained now, and they are moving with the leader. So to conclude my presentation, in this paper we have designed formation tracking algorithm in a distributed manner, and the multi-gen system subjects to various communication constraints, which includes the unavailability of all the states, which means we do not have velocity and input states. Secondly, the sampling periods among the agents are irregular and non-uniform, as well as asynchronous. In future, we will consider the formation tracking algorithm for nonlinear dynamics, and we will also study the case where we have measurement noises and external disturbances, etc. Thank you very much.